All right, let's go ahead and get this started. Oh, gravity. Hello, my name is Steve Jones, and I am a principal investigator and professional development instructor with Magnitude.io. Today, we're going to be talking about microgravity. What is it? What does it do? How does it affect us? And can we simulate it here on Earth? So first of all, in order to understand microgravity, you're going to need to understand gravity. Now, we've all experienced gravity. Gravity is a force of attraction between any two objects, and that operates across an infinite distance. So there is mass in the universe, so there's no such thing as zero gravity because gravity is everywhere. So gravitational acceleration. Acceleration is the change in velocity of an object. Gravitational acceleration is how gravity is affecting that object. Now, here on Earth, we experience what we call 1G. Why do we call it 1G? Because it's the only gravity that we've experienced as a species forever, well, at least until the last 50 years or so. Gravitational acceleration is dependent on where you are in the universe. Wait a minute. Can that be right? Wait. No, not hang on a second. Weight, Weight. How much you weigh is dependent on where you are in the universe because of the gravity of the object that is pulling against you with the gravity. So as that object is pulling on you, you feel weight. So here on Earth, we experience 1G. So our mass and our weight is right about the same number. Should be the same number. There are some minor differences depending on where you are in the globe. Actually, gravity fluctuates slightly, but it's not enough to really be perceived, so we don't worry about it too much. Now, you go to the moon. You go to the moon, there is gravity on the moon. The moon has about 1/6 of the gravity here on Earth. So, what does that mean for your students? Tell your students, think about how much they weigh. Let's say they weigh 60 pounds. They're really young students, very small. 60 pounds. On the moon, take that number, divide it by 6. They're going to weigh 10 pounds on the moon. So they're not weightless, but they weigh less. They haven't changed their mass. They didn't go on a sudden diet or anything. They just suddenly weigh less because gravity is not pulling on them as much. Think about an elevator. When you are riding in an elevator, if you're sitting still in the elevator, you feel normal. But if that elevator starts going up, you feel the gravity pulling you down because that force is pushing up on you. If you put a scale in an elevator and stood on that scale, weighed yourself, and you watch as that elevator starts to move, you're going to see your weight increase. Same as if an elevator starts going down, you're going to see your weight decrease. Then, the unthinkable happens, the cable snaps, and you're going to see it really decrease, and you're going to be what's called weightless because you are in a state of free fall. Just like a parachutist coming out of an airplane, you are falling. Now, what tells you you're falling? Is it the sensation in your body of I'm falling, I'm falling, I'm falling? Well, you're inside an elevator, remember? You can probably hear some noise outside the elevator. Uh, you can't see the sides going past you as you're falling. You can't feel any wind rushing past your face or anything. You can tell that you're not maybe touching something, but you can't tell you're falling until it comes to a stop. This was tested a lot of times in Niagara Falls when they would do the barrel over the falls activity. Now, again, don't try this at home, but people would actually get in a barrel, close the top of the barrel, and then get pushed over the falls. You don't have any sensation that you're falling until you hit the bottom. So that's what happens on the International Space Station as it's orbiting the Earth. The International Space Station is moving at a speed of 17,500 miles per hour. That's 5 miles per second. That's really, really, really fast. It takes 90 minutes for it to go around the Earth. Now, this speed was first theorized by Sir Isaac Newton in the late 1600s. He had gone away from Cambridge because of the plague, and so he had retired to his family farm and had started thinking about different things. And he came up with calculus. He came up with the laws of gravity and motion that we still study today. So he said, okay, if I took a cannon and I fired it from the top of a mountain, there was no air resistance to affect how this thing flew. The only effect on that cannonball should be gravity, which means the cannon is going to shoot the cannonball out, and eventually that cannonball is going to curve back to the Earth in a parabolic arc. So he started doing some more thought about this and started doing some math with it and theorized, okay, if I put even more powder and more powder and more powder into it, eventually I can get this thing going fast enough that it's just going to continue falling around the Earth until it gets back to where we started at, and it will never fall because it's moving faster than what gravity is able to pull it down towards the center of the Earth. He theorized that speed would be roughly 17,500 miles per hour, and that just happens to be what we use today.